Today we will discuss an important theorem on orthogonal projection operators. The theorem states that let Pm and Pn denote the projections on M and N respectively, which are subspaces of Hilbert space H, then Pm plus Pn is a projection if and only if Pn Pm is equal to 0, and in that case Pm plus Pn is P direct sum of M and N. We know that if Pm is a projection on M, that means Pm is an orthogonal projection operator on H and its range space is M. And similarly, Pn is an orthogonal projection operator on H whose range space is N. Then we have to prove that their sum Pm plus Pn is a projection if and only if their composition is the null operator. And we have also we have to show that the range of Pm plus Pn is direct sum of M and N. Let us prove this theorem. Let Pm plus Pn is a projection, that is, this is an orthogonal projection operator. So this is an idempotent. So Pm plus Pn whole square is equal to Pm plus Pn. And if we solve it, then we get here Pm square plus Pm Pn plus Pn Pm plus Pn square is equal to Pm plus Pn. And since Pm and Pn are projections, so they are projection operators, and so they are idempotent, and so Pm square is equal to Pm and Pn square is equal to Pm. And since Pn and Pn can be cancelled both the sides, so we are left with Pm Pn plus Pn Pm is equal to 0. Pre-multiplying by Pm in this expression, then we get Pm square Pn plus Pm Pn Pm is equal to 0. Here 0 is the null operator. Since Pm square is equal to Pm, so here we have Pm Pn plus Pm Pn Pm is equal to 0. Post multiplying by Pm in this expression, then we get here Pm Pn Pm plus Pm Pn Pm square is equal to null operator. And since Pm square is equal to Pm, so here we have 2 times Pm Pn Pm is equal to 0. That is Pm Pn Pm is equal to 0. If we put this in equation 1, then we get Pm plus Pn into Pn is equal to 0. So we have proved. We have to prove the converse part. So let us take Pm Pn is equal to 0. We have to show that Pm plus Pn is a projection. That means we have to prove that Pm plus Pn is an idempotent and this is self-adjoint. So take Pm plus Pn whole square, we get Pm square plus Pm Pn plus Pn Pm plus Pn whole square. And since it is assumed that Pm Pn is equal to 0, so here we have 0, and we have proved in the last lecture that Pm Pn is equal to 0 if and only Pn Pm is equal to 0, where Pm and Pn are projections. So both the terms here 0, and so we have here Pm square plus Pn square. But Pm and Pn are orthogonal projection operators, so they are idempotent. We have Pm plus Pn. So we have proved that square of Pm plus Pn is equal to Pm plus Pn. So Pm plus Pn is a projection operator. Now we find the Hilbert adjoint operator of Pm plus Pn. Pm plus Pn whole star is equal to Pm star plus Pn star. And this is equal to Pm. Why? Because Pm is an orthogonal projection operator, so this is also self-adjoint. And similarly, Pn is also self-adjoint. So we have Pm plus Pn. So we have proved that Hilbert adjoint operator of Pm plus Pn is Pm plus Pn itself, and so Pm plus Pn is self-adjoint. Hence, Pm plus Pn is a projection because it is a projection operator. This is also self-adjoint, so it is a projection. It remains to show that the range of Pm plus Pn is the direct sum of M and N. As Pm Pn is equal to 0, so M is orthogonal to N. This result we have proved in the last lecture, that if Pn and Pm is equal to 0, that means if Pn are orthogonal, then their range spaces are also orthogonal. So we have this, and from this we have M intersection N is singleton 0. As for each x belongs to H, image of x under Pm plus Pn is equal to Pmx plus Pnx. And since range of Pm is M, so Pmx belongs to M, and range of Pn is N, so Pnx belongs to N. So this element belongs to M plus N. So image of any element of H under Pm plus Pn belongs to M plus N. So we can say that range of Pm plus Pn is contained in M plus N. Conversely, we show that any element of M plus N is some image of some element of H under Pm plus Pn. So take some element. Let x plus y belongs to M plus N. X belongs to M and y belongs to N. Then we know that Pmx is equal to x. Why? Because we know that image of any element of the range under a projection operator is the element itself. Since M is the range of Pm, so image of x, since x belongs to M, so image of x under Pm is x itself. And since since N is the range space of Pn, so image of y under Pn is also y. As M is orthogonal to N, so N is contained in orthogonal complement of M. Why? Since orthogonal complement of M contains all those elements of H which are orthogonal to M. And since every element of N is orthogonal to all the elements of M, so N is contained in orthogonal complement of M. And similarly, M is contained in orthogonal complement of N. And in one of our previous lectures, we have also proved that orthogonal complement of range space is the null space. Since M is the range space of Pm, so orthogonal complement of M is the null space of Pm. And similarly, since N is the range space of Pn, so orthogonal complement of N is the null space of Pn. So, image of x plus y under Pm is equal to Pmx plus Pmy. But since y belongs to N and N is contained in the null space, so y belongs to null space of Pm. So Pmy is equal to 0, and here we have Pmx only. And image of x plus y under Pn is equal to Pnx plus Pny, but since x belongs to the null space of Pn, so Pnx is equal to 0, and here we have Pny. And consequently, Pm plus Pn of x plus y is equal to Pmx plus Pny. And Pnx is equal to x, Pny is equal to y, so we have x plus y. So we have shown that image of any element of m plus n is image of that element under Pm plus Pn. So the range of Pm plus Pn is m plus n. As m intersection n is singleton 0, so the range of Pm plus Pn is the direct sum of